the session. We appreciate everyone who's here attending. I think there's probably a few people that indicated that they would participate that aren't online yet. But we'll go ahead and start in the interest of time, because for those of you who just came on board, we've got to be off by 5 minutes till 10 Central Time, because another meeting is going to start within our GoToMeeting account here at NCAT. And I'm going to go ahead and turn things over to Stefan so he can brief us on their new facility there at the University of Texas at Arlington.
Buzz, thank you very much for this opportunity. It's a great pleasure and honor to present my new initiative to my fellow colleagues working on APT research. Good morning, everyone. So for those of you that do not know me, I'm Stefan Romanoschi. I'm an associate professor at the University of Texas at Arlington. And what I would like to discuss today, to present to you, let's see how this works. To present to you is our new initiative, the development of an APT research laboratory at the University of Texas at Arlington. This is a new initiative that took me about 4 years to develop. I joined this university in 2007, and since then, because of my experience and my trust in APT research, I decided to try to convince the university to develop an APT facility. In many ways, it follows the model of the APT facility at Kansas State University, in the sense that the facility is entirely owned and operated by the university. It's not it's not built with funds from the state DOT. So it was built entirely with internal funds. But to develop that, I will have to submit a proposal to my upper administration, and my major points was that we will be able to attract sponsor research from TxDOT as probably one of the main clients for us, and then local governments and industry. And also a big selling point for me was that for this proposal was that the center or the laboratory will be self-sustaining. In other words, we received an initial investment from the university, but for the future we will sustain our activity with funds we accumulate. And in many ways, this initiative was favored by the desire of the university to invest in the civil engineering department and in pavement research. I was faculty hire here in 2007, and I'm the first professor in the area of pavement and asphalt materials and concrete materials and mixes. So it was a desire to invest in this area even before I was hired. In the same time, another major selling point was the fact that there is no active accelerated payment facility in the state. So that means that we have a higher probability to attract research from state organization or local governments in the industry because of that. And in the same time, we had a dialogue with TxDOT, and TxDOT supported the idea of an APT facility. They did not provide any funds, they did not commit to provide any funds or research projects in the future, but they supported the idea. They said it's a good idea to have a facility in the state, and also that we will likely be attracting funds. And in my proposal, I highlighted the benefits of having an APT facility at UTA, and this was quite important because not many universities want to invest upfront so much funds and effort into developing a facility. But I convinced my administration that this facility will bring national and international prominence and visibility to the university, to the College of Engineering, to the Civil Engineering Department, will allow us to enhance the research in our department in the area of payments, research, transportation, geotechnical, and structural, and will allow us to be more competitive at the state and national level, to submit research proposals on topics that we have not done in the past, will allow us to collaborate better with other universities in the state, in the country, and even some other universities overseas, and will allow us to collaborate better with other departments within the university, and also to increase our graduate student enrollment. Lately, there's been a major interest from the university in expanding our doctoral programs. So having a research facility, having this magnificent research tool will allow us to improve our doctoral student enrollment. And in the same time, it will allow us to better serve our constituents and the state of Texas. And also in my proposal, I highlighted that it will be a self-sustaining investment and will be cost-effective. In my opinion, the path we follow is a very good path to follow for a university that is interested in developing an APT. But to develop an APT, you need several things. First of all, you need to have a good site. You need to have a site where you can build full-scale pavements, and you know, it should not be, first of all, should not be in a floodplain. If it is in a floodplain, you will have problems later, because the water table will influence, high water table will influence your results. In the same time, you have to have a reliable APT machine and efficient, capable of applying a high number of passes per week, and in the same time a machine that will not create, you know, will not break down often, and cost of the repairs to be maintenance to be minimal. You need to have dedicated research personnel. You cannot do APT research only with faculty and students. You need to have at least one or maybe even two technicians or even an engineer dedicated to this full-time. Then you need a sound business plan. It's very common these days that you go to the upper administration and request for funds. You are instructed to develop a business plan. And part of my business plan here, I followed the plan that we had at Kansas State University, is that we will charge the research client an equipment usage fee, which is quite common, not only in APT, but in many other research enterprises within the university. So, for example, if the university is interested in purchasing or constructing, for example, a telescope that is very expensive, or a very expensive microscope, it will have to charge the research client hourly utilization of that microscope, and even the National Science Foundation pays for that. So part of my business plan was that I will be able to collect enough equipment usage fee to become a self-sustaining enterprise, if you wish. And of course, a major importance to the success of having this proposal come to life is to have support within your own organization. You have to have somebody in the upper administration that is believing in your proposal and shares your enthusiasm. And it also helps if you have some potential clients. If you have a first project, is obviously a significant help. We did not have a first project at the time that this process started, but when we had the project with TxDOT was awarded to us, the entire development of the APT laboratory accelerated. So first of all, we need an APT testing site, and our site, if you are familiar with the Dallas-Fort Worth area, so you have the Dallas on the city on the east side and the Fort Worth on the west side, and somewhere between the two you have the airport here, Dallas International Airport, Dallas-Fort Worth, and the UT Arlington is almost mid-distance between the downtown Dallas and Dallas-Fort Worth. The facility is on university-owned property, is on the east side of Fort Worth. It's about 10 miles drive from the university, about 15 minutes drive. So it is in the area that a piece of land that is owned by the university is somewhere here in this part. And if we look at the satellite image, it is across the street from a research institute that belongs to the university. And also we selected this location because we have a large asphalt plant. You can see it on the left of the screen, and that is in the vicinity, and that will help us with the production and placement of the asphalt mixes. And the land is not very large, but it is on the university-owned property. And I submitted a schematic of what I needed for the facility, and essentially this is a simple diagram. You need a fence around the property. You need the testing pad or experimental area where the pavement sections will be built. And I followed in many ways the way the APT facility in Louisiana is organized. And I decided from the beginning to start with the trailer, and later on maybe to see if I can expand and eventually build a permanent building. And these are some more images on how the site looks like, or the plans, some other rendering images, and these are some photographs of how the site looks today. So this an area that is fenced, and in the middle is the testing pad where the experimental sections will be built. We already have the office trailer, so everything is there already. And obviously you need to have all the utilities at the site, so you need to have electric power, sufficient electric power to run the machine, to run the trailer, and also to have room to expand if you need to do it later. You need to have a water source, you need to have a telephone line and internet cable line, and so on, and sewage system. Regarding the pavement testing machine, we decided to be able to reduce the cost was to design and build the machine ourselves. And I designed a machine that is linear, simply because you have a low probability of failure, is relatively easy and cheap to maintain and repair. I designed the machine to be mobile, so it will be towable to remote sites if you need to do testing in a remote location. And also, if you make it mobile, when you move it from one test section to another, you don't need to rent cranes, and that helps. The pavements that you need to build, the experimental section, will be straight and can be built with conventional mentors and equipment. So that makes me decide to go with a linear APT machine instead of circular machine. It occupies less space, and you also can move it indoors if you have the pavements built indoors in a building that obviously can accommodate a machine of this size. This is a photograph of how the machine looks on the outside, but in principle it's just a testing frame. It's very similar in principle with the one existing at Kansas State University, and somewhat similar to the machine that is at Purdue University, and many other machines. The HVS and the Atlas are kind of similar in principle. But what we also did, we built a temperature control chamber around the machine. We will attempt to control the temperature underneath the, inside the machine, so we can control the temperature at the surface of the tested pavements. And this is critical when you are testing asphalt pavements. You have to control the temperature quite accurately. This is a photograph showing the machine inside. So the principle is very simple. We have a bogie essentially that is pulled back and forth, and a large steel frame that uses it's a heavy frame, and the frame is a reaction frame. So the bogie is pulled back and forth, and it has a hydraulic system that pushes the bogie down, pushes up into the frame. Because the frame is so heavy, it will apply the load to the pavement. And the loading is applied with a full-size single track axle, and that allows us to test two pavements at a time. And just to give you an idea of the scale, we have full-size track axle, so this is a full-size pavement tires. For this experiment, the first experiment, I proposed to go with a bus tire that has a higher capacity, about 9,000 pounds maximum load per tire. So in case later in future experiments we will go and apply these high loads, we will be able to compare the results. In the same time, the whole machine moves transversely on a support system, and we can change to apply the lateral wonder. We can change the lateral position. It's programmed. At the moment, we have programmed it to follow a truncated normal distribution. But there are several normal distributions that can be applied. You can also apply, uniform distribution, so the same number of passes is performed in each lateral position, and is moving the whole machine in half-inch increments. So in terms of the capability of the machine, 2 pavements will be tested at the same time. We'll run 24 hours, 7 days per week. We'll apply probably around 120,000 axle repetitions in a week in bidirectional mode, and half of that in unidirectional mode. So the hydraulic system, if you want to apply loading in unidirectional mode, it will lift the axle off the ground. When it goes one direction, it will drop it back on the ground, apply the load, and then lifts it back. The design load is up to about 36,000 pounds per axle. The design of the bogie itself, it can handle 40,000 pounds per axle, but I don't envision that we will go nowhere near that, because we will fail the pavements too quick. The loading speed is somewhere between 7 and 10 miles per hour. In the first experiment, we will start with 7.5 miles per hour, which is the speed used by the HVS machines. We build a temperature control box. We will try to control the temperature within plus minus 2 degrees Celsius. We hope to be successful on that. And some of the features can be moved indoors or towed to a remote location and occupies less space. The machine now is about 68, 70 feet long and about 10 feet wide. And as I mentioned to you, the fact that TxDOT has awarded to us a project speed up the development of the facility. The first project looks at the maximum allowable amount of recycled binder, RAS and RAP in the mixes using APT. So the Texas project started in May this year, will continue for 2 years. The title is Validation Maximum Allowable Amounts of Recycled RAP and RAS, and we are aiming to validate the maximum allowed percentages of RAP and RAS in the TxDOT specification. This idea was generated from the fact that there have been several projects in Texas where the mixes have been placed following this specifications, but some failures have been noticed, and because of that there was a need to revise to see if the values in the specification should be changed. In this project, I'm working together with a group of researchers from the TTI, with Tom Scullion being their lead person there. The objective of the study is to establish an APT facility in Texas. It was not really part of the project, but I think the intent was to help with that, but to validate that poor results on the lab prepared RAP and RAS samples translate to poor field performance. Again, there have been some projects where actually in the lab the mixes did not show very good performance, but they performed well in the field, and vice versa. In the field, they perform bad when the mix design actually indicated that the mixes will perform well. We also have in Texas a software that is developed by TTI to predict mix cracking and rutting in overlays, and part of the project objective is to validate that overlay design tool. And also we want to investigate if balanced mix design procedures can be used to design RAP and RAT mixes with performance comparable to virgin mixes. I don't think I should go much in detail discussing the balanced mix design, but the idea is when you design a mix is to perform Hamburg wheel RAT test and also the overlay test, and from those two tests, you'll have information on what is the optimum design for optimum binder content that will lead to sufficient resistance to rotting and cracking, and then to find the common ground binder content between those two limits for which both rotting and cracking conditions are, resistance to cracking and rotting are satisfied. So the work plan is quite simple. Obviously, we'll start with the literature review, followed by the planning of the experiment. We already did submit a detailed plan of how the APT experiment will be done, and some of those information I'll present today. We had a kickoff meeting in May. We had several meetings with the technical panel since then. The APT facilities is pretty much established. We are working right now on finalizing the machine. We have conducted lab mix designs to come up with the design of the mixes that will be placed for this, built for this experiment. Hopefully this month we will do the construction of the asphalt layers, and then in January or February we will start the APT testing. And obviously after that we will analyze the results, develop the recommendations regarding the maximum allowed percentage of RAP and RAS in mixes, and then we will draft the final report. For this project, we have started the construction of the sections. This is the experimental design, if you wish. So part of this experiment, we will test the 12 pavement sections. We test sections 2 at a time. So in this experiment, we are looking at testing 4 different mixes. I will get back to that in a minute, but each mix will be tested in 3 experiments if we wish. We will have a rotting experiment, we will have this sections H, I, J, and K, then we will have a fatigue cracking experiments, F, E, L, and G, and a reflection cracking experiment. So this section will have different thicknesses, will be tested at different temperatures, with the idea of comparing these 4 surface mixes, compare the performance of these mixes for reflection resistance to reflection cracking, fatigue cracking, and also rotting. For the reflection cracking section, what we plan to do is to make some saw cuts into the intermediate layer and the base layer and place a surface layer on top to make sure that the deterioration on the existing pavement underneath the overlay is the same in all 4 sections. The sections are about 75 feet long, and they are about 8 or 10 feet wide. The sections that are at the on the sides of the experimental area are a little bit wider to avoid the edge effects. So we have constructed the foundation layers. We have brought soil from good soil from a pit for the top 3 feet. So we have excavated the existing soil. We have added new soil to make sure that the foundation is the same for all sections. Then we tested for density. We tested for stiffness using the light falling weight and using the falling weight deflectometer. These are, for example, some of the results. We have done 3 measuring stations in this location. In the location where the testing will be done, and we have noticed some variability in the measured stiffness of the subgrade. That may be caused by the fact that we tested it after a few days after the rain, and the moisture content was not uniform over the entire site. But we will repeat the test after the pavements will be built. We will do falling weight deflectometer test to estimate the modulus of the subgrade layer. After that, we constructed the base layer. I will show you the thickness of the sections. The base layer for some sections is made of soil cement. For other sections, it's flex base, so it's granular material, crushed rock. So we have built it, the base layer. We have compacting it to standards. We actually had a very good soil that was mixed at the plant with 3.5% cement and transported to the site and spread out and compacted. We measured the density after the compaction, and we have covered the the base with a tack coat. We have placed a tack coat just to make sure that we are curing the base properly. I'm not sure, depending on the resolution, if you can see that actually the materials are different. So in this area you have the crushed rock. This is for the fatigue sections. For the fatigue sections, yes. On this side will be the rotting section, and on the other side will be refraction cracking sections. These are the thicknesses for the layers. So for example, in the reflection cracking, we will have the surface layer 2 inches with 4 different mixes, then an intermediate layer with 2 inches, and then a cement treated base 8 inches. In a fatigue cracking, we will have a surface of 2 inches, a base, flex base of 8 inches. This is already placed, and below that we have placed a cement treated sub-base with only 2% cement. In the rotting experiment, we have the same 4 mixes that we are studying. I'll discuss about the mixes in a minute. And then we have a coarser mix for the intermediate layer. It's a type B mix, which corresponds to I think a 25 millimeter superfave mix. Then we have cement treated base. So the 4 mixes that we will study, we will place a mix that is a conventional mix design for the surface mixes. It's a mix that is produced here by that plant for several projects in the area. Then a mix that has 19% wrap, we call that high wrap mixes, so it has only wrap. Then a mix that will have wrap and RAS. And then the last mix is to validate the balanced mix design. So those are the 4 mixes that we will place. Both the intermediate mixes for the intermediate layers, the type C and the type B, will contain wrap. We found out that this plant is using wrap in almost all the mixes that they are producing. So their mix design that they give to us include wrap in these mixes. So after paving, during paving, we will check the quality of the construction.
Hey, Stefan?
Yes.
This is Buzz. Can I ask you a question?
Yes.
The asphalt plant, is that a privately owned asphalt plant or a state-owned asphalt plant?
It's a privately owned. It's quite a large plant, yes. The company name is Austin Bridge and Road. They own several plants in the Metroplex.
Just from an administrative point of view, did the university allow you to set up like a sole source arrangement with them to provide mixes for your test sections?
Yes. I mean, I just had to fill a page with the sole source justification, and justification is very simple. The client, in our case TxDOT, has selected this plan.
Okay.
And we went with that. But you know, the quantities are not very large, the quantities of the mix. Maybe I should discuss a little bit. You saw earlier the dimensions of the sections. So if you look at each section, for example, each mix, we will need roughly about 50 tons of a mix, to somewhere between 40 and 50 tons for this. I'm talking about the 4 mixes for the surface layer. And we have decided to purchase 100 tons of this mix because we want to make sure that the contractor has can achieve, you know, the mix design that we want. For the intermediate mixes, the intermediate layer mixes, they are commercial mixes, so they will sell those mixes to clients in town. We will have a compaction roller that will come here to be instrumented compaction roller to look at the number of passes applied to test sections and how the density of the mix increases with the stiffness of the mix increases with the number of applied passes. After the construction, we will use a GPR to determine the thickness of the layers. We will take cores to check for the uniformity of the mix and for the thickness of the mat. We'll use nuclear density gauge to check for air voids, and everybody does this. It will take sufficient samples of the mix for all future lab tests, and Also, we will try to store some of the original materials. Maybe somebody else, not necessarily us, will try to use our results, and also we'll need to do some tests on these materials. And we will do falling away deflectometer tests right after construction to use the back-calculated moduli to import them in our models to evaluate the number of passes that we estimate will need to fail the sections, and also look at the load transfer on the so-cut sections. The plan for material testing, we will look at testing the aggregates, classical test, gradation, particles, percent fine, cellular abrasion, and coarse and fine aggregate angularity for bituminous binders, the shear modulus and phase angle at 7 temperatures. For the asphalt mixes, we will collect mixed during construction to determine the binder content, the aggregate gradation. We'll do the Hamburg wheel rat tester test on the samples of compacted samples in the lab, and also on course. The same for the overlay testers. We will cut beams to perform the beam fatigue test. We will also, TTI will do the permanent deformation test. It's a test required for the overlay design programs, and we also do the dynamic modulus test at 2 temperatures. In terms of the plan for APT testing, the fatigue sections and the fatigue cracking and reflection cracking sections will be tested at the target temperature at the pavement surface of 20 degrees Celsius. The ratting sections will be tested at target temperature of 40 degrees Celsius. We will start with testing the fatigue cracking sections in the spring next year. In the summer we will test the ratting sections, and in the fall we will test the reflection cracking sections. That's the plan, because we will try to test obviously the ratting sections at higher temperature, so we'll be able to control that temperature if we test it. We'll control it better if we test it in the summer. We plan to apply bidirectional trafficking for the fatigue cracking and ratting sections, and unidirectional trafficking for the reflection cracking sections. At the moment, we're planning to use the single axle load of 18 kip, but again, the analysis will tell us, depending on what's the number of passes to failures, if we need to increase the load or not. But the plan is not to increase the load during testing. So we will decide from the very beginning what is the axle load that we will go with, and we'll stay with that until the pavements will fail. And 100 psi tire inflation pressure, and we'll apply lateral wonder. The maximum lateral position left and right is 12 inches. The standard deviation in a normal distribution is 8 inches, so we will cover about 94% of the area underneath the normal distribution curve. Regarding pavement monitoring, we will monitor performance of the pavement. We measure cracking and ratting, but we will stop testing when we will achieve 3/4 inch of rat, or when we achieve 25% of the lane area is cracked, which is equivalent to 50% of the traffic area cracked. And we will measure response and the condition of the pavement during testing. So the monitoring plan includes measuring the transverse profiles in 3 locations, doing the crack mapping. From the beginning, we don't have an automated system, so we will do a manual crack mapping. We will measure longitudinal transverse strains at the bottom of the asphalt layer with 2 strain gauges, and also we have load cells installed on the axles to measure the load applied by each wheel, so the dynamic load. We'll measure temperatures. We'll record it every 15 minutes in 2 locations, and the surface in 3 different depths within the layers. We also have TDR moistures installed to measure the moisture at the top of the subgrade. So the plan is to measure the response right before APT loading is starting, then at 5,000 passes, 25, 50,000, 100,000, and then every 100,000 passes after that, which corresponds to about 1 week of testing. This is just a schematic of the location of the sensors. So the sensors for the fatigue and rotting sections will be placed at the bottom of the asphalt layers. These are the longitudinal and transverse strain gauges. TDR gauges installed in the subgrade, and temperature sensors installed, thermocouples installed at several depths in the asphalt layer. Now, a little bit different will be the configuration, the location of the gauges in the reflection cracking sections, because we will try to avoid the saw cuts. We need to stay away from the saw cuts. So these are the sensors. We have received very good advices and help from Buzid's research group, from Florida DOT, and also from Louisiana DOT and the Ohio facility in terms of the selection of the strain gauges and the design of the data acquisition system. In terms of non-destructive testing, we plan to do falling weight reflectometer test before loading, APT loading is started, and then after 5,000 passes, after 100,000 passes, and then at the end of the loading. And we will also have PSPA here to test periodically with the objective of determining the duration of the asphalt concrete to see how modulus of the asphalt changes. And when the pavements will fail, we will conduct the post-mortem analysis to investigate the failure mode and the cause for each failure. We will cut a trench, one transverse trench in each section, and we will measure the transverse profile at the top of the asphalt layer, at the bottom of the asphalt layer, hopefully, if we can, at the interface between the base and the sub-base, to be able to identify how much of the surface rotting comes from each layer. And we will do coring of the asphalt concrete in and outside the traffic areas to be able to see if there's any change in density, and also maybe to see if there's any change in the stiffness of the binder. Again, we are not up and running yet, so for the moment we are in the process of finalizing the construction of the sections and finalizing the machine, and we hope that we will be operating, start testing in January, February. So right now I think, Buzz, if we can open for questions or comments or suggestions. How we are doing on time?
We're doing well on time. We've got about 10 minutes, and there's a chat question has been submitted. Can you see that, Stefan, on your screen?
Yeah. The question is if we will use pass or fail, remove or replace. This is probably referring to the pass or fail removement of the past constructed sections. What we will do is, our plan is to collect all the information after the sections are built and submit that information back to the technical panel, and also on our end to come with a proposition if we accept this material or not. But the plan is, again, to purchase about 100 tons of each mix, is to start placing some of that mix around the experimental area in the testing pad until we feel confident that the mix is what we designed. We won't allow the contractor to come and place on the experimental sections.
Stefan, I have a question regarding that, or maybe a question and a comment.
Yeah, there's another question here, is what is the temperature heating range of your chamber? In terms of the lower temperature, obviously is you have to kind of go with the seasons. So in the summer you can probably go close to about 50, maybe a little bit more than 50 degrees Celsius inside. In the winter probably you cannot go lower than 10 degrees Celsius and higher than 30 degrees Celsius in the winter. Yes, Buzz, I'm sorry.
Your lower layers of asphalt, under your test sections, you said those are going to be standard TxDOT mixes?
Yes, the intermediate mixes, yes.
The intermediate mixes, I would expect those mixes to be relatively easy for the contractor to produce because those should be mixes that they have experience with. The treatment mixes in the study, are these going to be new mix designs, or are these going to be mix designs that the contractor might have experience with?
One of the mixes, and maybe I should go to that slide, one of the mixes is a mix that has been produced already by them several times. So we started with the mixes type D mix. Right. It's a mix that they have produced already. And from that mix design, we have created the 3 other mix designs.
I would, if I were doing these, and I know you've got a lot of experience, and a lot of people in the web meeting have a lot of experience, but if I was doing these, I would be cautious about the quantities that you have set up for any mix variant that is a new thing that the contractor doesn't have experience with, and I would plan on more quantities, because like before we put anything in a test section, I'll do a trial mix run and evaluate it extensively in the laboratory. And a trial mix run, for me to get a good truckload of material to sample from, I've got to run 3 truckloads of material with a little bit of uncoated waste on either end of that because of variability in quality during startup and shutdown. So I would plan on much greater quantities for those mixes in order to try to avoid having a remove and replace scenario, or have a judgment call where you've got some properties that maybe aren't quite what you want them to be in your test sections.
Buzz, you're right. I mean, we will try our best. You know, we feel that from our discussion with the contractors that those 100 tons would be enough, but you know, we cross our fingers and hope something bad is not going to happen. But
like if I was running those mixes, I would plan on 75 tons in 2 practice runs in order to make adjustments to the mix to get exactly the lab properties that I wanted. So that's 100. That would be 150 tons before I ever put anything in a test section, and then in the test section, I would have 25 tons of waste on either end of the production run for what I placed in the test section. That kind of is my standard operating practice down here, and I know probably we all have our standard operating practices, but that would be the feedback that I would give you.
Thank you, Buzz.
Nelson, you got a couple of more chat questions, I think, there, Stefan.
Hello?
Hello? Hello?
Yes, I just didn't hear him quite right when he was talking about the temperature chamber, what the maximum you can heat to.
Yeah, I think the air inside, it can be heat to about 50 degrees Celsius.
Oh, okay, 50 degrees Celsius.
Can you see the two chat questions that have been submitted, Stefan?
Let me see. How did I pick the 40 degrees Celsius? I think if you try to run it at a higher temperature, you will fail the pavement too quick. You know, you will get rotting way too fast, and because of that, you know, it will not be representative of what's happening in the field, and probably you won't be able to get the right comparison between the mixes. But it is very likely that when we will do the Hamburg wheel rot test, we will do it at 50 degrees Celsius, but also at 40 degrees Celsius. We'll do it at the temperature. We will do the rot testing in the APT experiment.
Stefan, the only other comment that I would make is regarding the the load level in these mixes. And regarding your laboratory testing plan, as you know, because I've discussed it with you in the past,
Yes.
we continue to find that the performance of higher recycled content mixes is dependent on the strain rate in terms of cracking performance. It's highly dependent on the strain rate. So it was really encouraging to see that you haven't set your test plan up to superload these sections, because under superloading with much higher strain rates, unrealistically high strain rates, I'm sure you would find crack susceptibility, high crack susceptibility in the treatment test sections. And we're experimenting here at NCAT with varying the overlay tester procedure and using lower strain rates, a range of lower strain rates, to try to extrapolate and predict crack susceptibility at the extremely low strain rates that you actually see on the bottom of pavements. So that, just as a word of caution, the testing that we're doing, it looks as if it's continuing to confirm that observation for us.
But it's a very good comment in the sense that we plan to go at the moment with the standard axle 8 and to keep the strain relatively low. The intent is to have not to have the failure of some of the sections, for example, the fatigue sections, in less than 1 million applied cycles. We don't want to apply high load and get the failure quick. That's not our plan.
Right.
So the estimation and the allocated time is to apply about 1 million cycles to failure to the standard mix, and obviously for the other sections, the other mixes will have to see how they perform. But from the very beginning, this was our intent. We don't like the idea of failing the pavements too quick.
Well, and I would also encourage you in your laboratory testing plan to take a look at varying, doing some additional overlay tester testing using very small gaps, very very small deformation or displacement levels in the device, because if you're not using extremely high strain rates on your test sections, because you shouldn't on your test sections, then that's going to be the source of a huge disconnect between what you observe in your test sections and what the overlay tester predicts in the laboratory.
Yes, I'm sure you're right. I have noticed that in some of my past projects, the fact that ranking of mixes in terms of fatigue performance changes if you test those mixes at low strain or you test it at high strain.
That's right.
Even in big beam fatigue tests, it will show you that.
And that's a different type of strain in an overlay tester, but the standard test method, I think, is something like 40,000 microstrains, where you're you're several hundred microstrains probably in most of the work that you're doing on these sections. So that's a huge disconnect.
But if I may ask, based on what you are saying, so what range of displacement in the overlay are you currently using? What
we're experimenting with is dropping the rate progressively lower in overlay testing, and just taking it as low as we can go and still control the experiment properly, and then extrapolating that out to very low strain levels. So essentially plot it on a log-log scale and draw a line through it, and then predict down at very low strain levels what you would expect to see. And in the commercial overlay testers, that's very hard to do, but what we hope is that there's now a jig that you can get for the AMPT machine that allows you to run an overlay tester type test in the AMPT machine, and we're hoping that we can use it with very low strain levels to get much closer to the scale that we're observing in our test sections.
Okay. Yeah,
what we have done, we have have done a preliminary estimation of number of passes to failure for this axle and for some selected properties for the material for the foundation. And this is how we came with this layer thicknesses. So we kind of design already the sections estimating that we will fail the sections around 500,000 cycles in rutting and about 1 million cycles in fatigue.
Everybody, I really hate to cut us off here, but Stefan has agreed to do kind of a part 1, part 2 series on his new program. And Ben, I think you probably would agree with me. It's kind of neat to have a series of presentations on the birth of an APT program. It's kind of a unique, most of the time when we talk about our programs, we're talking about, it's from a historical perspective, and we appreciate Stefan sharing the birth of his program and the development of his program. And we got to end it here to make way for the next meeting that's fixing to start. But we appreciate everyone participating, and Stefan, we appreciate your time, and we'll look forward to your next presentation.
Thank you very, very much.
Thank you, Stefan.
Everybody have a great day.
Okay,
Thank you.